We want to determine the pH of our solution after adding 5 milliliters of titrant. At this point, you have both base and conjugate acid present in your solution, so this is a buffer problem. We want to know the pH of the titration after adding 5 milliliters of 0.0998 molar HCl. We first determine the moles of each component. For our A-, we have 10 milliliters times its concentration, and we get 0.0022 moles. For H3O+, we have the 5 milliliters times 0.0998 molar, and we get 0.0005 moles. Now we use our BAA table, which has moles, not molarity, and we put in all our values. We're going to subtract our quantity of H3O+ on the left and add it on the right. So after our addition, we have 0.0017 moles of A-, no H3O+ remaining, and 0.0005 moles of HA. Now we can use the HH equation. We calculated pKa in the previous presentation, so we have 10.34 plus the log of the base concentration divided by our acid concentration, and we get 10.87. Now we're going to find the pH at the equivalence point. At the equivalence point, A- and H0+ are limiting, so the solution primarily contains the conjugate weak acid. Let's find the pH at the equivalence point if 21.40 mils of our acid are required to titrate 10 milliliters of unknown base in 40 mils of water. So first we're going to determine HA at the equivalence point. To do this, we're going to find the moles of A- and assume all of these were converted to HA. So we take the concentration of A-, multiply by the volume we used, and divide by the total solution volume. So we have 0.220 molar times 10 milliliters divided by the 71.4 milliliters, and we get 0.0308. Now we can put this in an ICE table to solve for the equilibrium concentration of H3O+ using the Ka value for this acid. So we know that Ka is 4.6 times 10 minus 11. We set that equal to x squared over 0.0308, assuming x is small. Then we can solve for pH. So we have pH as the negative log of the x value we found in part 2, and we get 5.59. Now we want to calculate the pH 2 milliliters after the equivalence point. We will have excess HCl after the neutralization step, so we can convert this to the concentration of H3O+ and then get the pH. So we want to know the pH of the titration after adding 2 milliliters of 0.0998 molar HCl past the equivalence point. So at this point we've added 23.40 mils total to 10 milliliters of unknown base in 40 mils of water. So first we determine the moles of each component. So we have 10 milliliters of our base, so we get 0.022 moles, and 23.4 milliliters of our acid times the 0.0998 molar, and we get 0.00234 moles. Now we use our BAA table. The only trick here is that now our limiting reactant is our A-, not H3O+. So we're going to subtract 0.0022 moles from A- and H3O+ and add it to HA. So after the addition, we have no A- remaining. We have 0.00014 moles of H0+ and 0.0022 moles of HA. Now we can find the H0+ concentration and the pH. So we know the H0+ concentration is equal to our excess moles of HCl divided by the total solution volume. So we have 0.00014 moles of HCl divided by 0.0734 liters of solution, and we get 0.0019 molar. So we can take the negative log of this concentration to get pH, and we get 2.72. We can ignore the HA because it contributes a negligible amount of H3O+ relative to how much H3O+ we get from HCl.